We now continue our study of hypothesis testing on the mean. So first thing we need to do here is recall when we worked with confidence intervals, we had to decide whether we needed to use this margin of error formula or this margin of error formula. This one was based on the standard normal distribution curve, hence the z sub c critical value. Again, this was a result of the central limit theorem. Or down here, we use the t sub c critical value that was associated with the t distribution or the student t distribution. So you didn't just randomly pick whether you were going to use the formula built off of the standard normal distribution or the formula for the margin of error built off of the t distribution. There were conditions under which you would use this one or you would use this one. And these here are the conditions. So use the standard normal distribution as part of our computation for the margin of error when computing confidence intervals if the population standard deviation sigma was known and one of these two things had to be true. N had to be greater than or equal to 30 or the population had to be approximately normally distributed. If that was the case, so you have sigma known, and then you have one of these two things known. Either n is greater than or equal to 30, the sample size is greater than or equal to 30, or the population was normally distributed or approximately normally distributed. In that case, we use this formula, we use the standard normal distribution to get the critical value z sub c. In the other scenario, if the population standard deviation is unknown, and also the data is approximately normally distributed or n is greater than or equal to 30, then we use t sub c in our formula, the critical values from the t distribution. So the difference between these two conditions for which you would use the standard normal distribution or the t distribution is whether sigma is known or whether sigma is unknown. These same two conditions are what we need to closely pay attention to when doing hypothesis testing on the mean. They are going to determine whether you're going to use the standard normal distribution or the t distribution in the process of doing the hypothesis testing. Let's take a look at how they apply. When doing hypothesis testing on the mean, we need to decide, are we going to be doing a z-test or a t-test? Z-test is referring to using the standard normal distribution in the process. T-test refers to using the t distribution in the process. So here are the two scenarios. You've got if the population standard deviation sigma is known and n is greater than or equal to 30, or the population is approximately normally distributed, then you're going to conduct a z-test. These were the same conditions for which you used the z sub c critical value when finding margins of error with confidence interval. So in these scenarios, you're going to conduct a z-test. And a z-test has a standardized test statistic of precisely this. Z equals the difference of x bar and the hypothesized mean over the standard error, which is the population standard deviation divided by the square root of the sample size. Now, the other scenario, if the population standard deviation is unknown and the data is approximately normally distributed or n is greater than or equal to 30, then you're going to conduct a t-test. This is, again, the exact same conditions under which we use t sub c as the critical value in the margin of error computation with confidence intervals. So if these conditions are met, then we conduct the t-test, which has a standardized test statistic of t equals x bar minus mu, that quantity, over the ratio of the sample standard deviation to the square root of the sample size, with, of course, n minus 1 degrees of freedom. This parallels exactly what we did with our confidence interval computations. Now that we've established the conditions for which you would use a z-test or a t-test, we can now get back to specifically looking at the critical region approach for hypothesis testing on the mean. This set of videos is going to focus specifically on using the critical region approach. The next set of videos will focus on using the p-value approach for hypothesis testing on the mean. So let's first recall the critical region approach. Again, it's the 6-step process. In step 1, we define our pair of hypotheses. One is the null hypothesis, the other is the alternative hypothesis, and they are complements of one another. The null hypothesis is the one that has the equality with it. Remember that the claim can be either the null hypothesis or the alternative hypothesis based on what claim they're making in their statement. Step 2 is to note the level of significance alpha, which again is given to you. Alpha is the likelihood of committing a type 1 error. That will be given to you in each problem. Step 3, we need to determine the type and tail direction of the test. Recall that to find the tail direction of the test, you need to refer to H sub A, the alternative hypothesis. If in the alternative hypothesis you have mu is less than something, then you've got a left tail test. If you have mu is greater than something, then you've got a right tailed test. And if you have mu is not equal to something, then you have a two-tailed test. What we mean by determining the type of test is whether you're doing a z-test or a t-test. And the conditions on which you can use a z-test and when you can use a t-test were on the previous screen of this video. Once we've completed step 3, then we can draw and label the appropriate probability distribution curve based on the type of test you're performing. So if we're doing a t-test, we're going to draw a t-distribution. If we're doing a z-test, we're going to draw a standard normal distribution. And when we do that, we're going to shade the tail in the direction determined in step 3. So if you're doing, for example, a right tail test from step 3, then you would shade the right tail in the picture. The shaded region is what we call the rejection region. The area of the shaded rejection region is precisely alpha, which is, again, determined up here. Then we need to find the value that separates the rejection region from the fail to reject region. And we got to label all this information on our graph. Then in step 5, we compute our test statistic, which is what we saw on the previous screen, and then we make a conclusion on H naught. If your test statistic falls in the rejection region of your graph in step 4, then you're going to reject H naught. If your test statistic falls in the fail to reject region, then you're going to fail to reject H naught. Again, hypothesis testing is done under the assumption that the null hypothesis is true. That's why we focus here on whether we should be rejecting the null hypothesis or whether we should fail to reject the null hypothesis. Once you've done this, we then need to go back and make a conclusion about the claim and interpret our results. So just because, let's say, for example, that you're supposed to reject the null hypothesis according to your test, that doesn't mean you're going to reject the claim necessarily. If your claim is the null hypothesis, then yes, you would do the same thing. So if you rejected the null hypothesis and your claim was also the null hypothesis, then that means you're going to reject the claim. But let's say you rejected the null hypothesis and the claim was the alternative hypothesis. If you're rejecting the null hypothesis, then it means you're failing to reject the alternative hypothesis because they're complements of one another. So we need to make a decision about the claim, and always, 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 we got to write an interpretation of what all this means for this specific problem. Let's now look at an example that we originally started in the introduction to hypothesis testing videos, and now we'll be able to finish it using the critical region approach, hypothesis testing on the mean. Now return to this example. So a cell phone manufacturer says its average battery life is 24 hours. We randomly collect a sample of 50 of their phones and test their battery life. The average battery life of our sample is 23.2 hours with a standard deviation of 0.9 hours. At 5% level of significance, should we believe the company's claim? So based off of our sample data, should we believe their claim that the average battery life is 24 hours? So this is hypothesis testing on the mean, and we're again going to be using the critical region approach for this problem. So this actually here we already did in the previous video, but let's recall this. So their claim, which is this right here, is that mu is equal to 24. Now, don't even worry about whether that's the null hypothesis or the alternative hypothesis yet. First, write down the complement of mu equals 24, which is mu is not equal to 24. Then, the one with the equality, which is this one here, is always the null hypothesis, making the other one the alternative hypothesis. So that's what we've got here in step 1. Step 2, you're going to simply make note of the significance level. Again, that's always given to you. So this is at 5% level of significance, meaning with our test, we're willing to take a 5% chance of committing a type 1 error. Then in step 3, we already determined that we are going to be doing a two-tailed test. And again, the way to determine whether you're doing a left tail, right tail, or two-tailed test is to look at the alternative hypothesis. And in the case where mu is not equal to, that means we're doing a two-tailed test. That means there's going to be a rejection region on the left-hand side and on the right-hand side. This is where we left off. Now we can actually add in the type of test. So step 3 is not only figuring out which direction the rejection region tail is in, but we also need to say whether we're doing a z-test or a t-test. So based on this information up here, let's write down some of it. We have a sample of size 50, that's n, and The average battery life of our sample is 23.2, so that's about the sample, so that's X bar. And with a standard deviation of 0.9 hours. Again, this 0.9 hours is referring to the sample of the 50 phones that we tested. So that is S, not sigma. Remember, S is the sample standard deviation, sigma is the population standard deviation. So in this problem, we do not know the population standard deviation sigma, hence we cannot use a z-test. We may be using a t-test. A t-test, the population standard deviation needs to be unknown, which is the case here, but then we also need sample sizes of 30 or greater, or we need to know that the data distributes normally or approximately normally. And actually, in this case, we have a sample size of 50, which is clearly greater than or equal to 30. So it is official. Since the sample size is greater than or equal to 30, and we do not know the population standard deviation sigma, that means we can do a two-tailed t-test. So we're doing a t-test this time, not a z-test. Let's now move on to step 4. Again, as a reminder, step 4 in the critical region approach is to draw and label the appropriate probability distribution curve based on the type of test you're performing. And then we have to do all this stuff here, which we'll get to in a second. So on the previous screen in step 3, we saw we need to do a t-test. So this is a t-distribution we're drawing here. So of course, you know that the mean of the t-distribution is 0. And now, which tail are we shading? In step 3 on the previous screen, it said we were doing a two-tailed test. So that means we're shading in a left tail and the right tail. So we've got a two-tailed test here. Remember, these two regions out here that are shaded, these are the rejection regions. Ultimately, what that means is if our sample statistic, which is what we compute in step 5, if it falls out there, then that's too extreme and we want to reject the null hypothesis. But let's back up a second. We're not quite there. Let's finish labeling this graph. Now, your rejection regions out here and your fail to rejection regions in here, or just for simplicity, again, they're not exactly the same. I'm going to call this the acceptance region. So our rejection regions are out here. This is our acceptance region. So the key thing that we need to know is what is this t-value and what is this t-value here. These two values here separate the rejection region from the acceptance region. Notice, because of the symmetry of the t-distribution and the fact that it's centered at 0, these two numbers are going to be opposites of one another. We need to get these critical t-values from the t-distribution table. When we last used this, the column that we were in was determined by the level of confidence. Now, in this case, it's going to be determined by the tail and by the level of significance alpha. Now, if you were doing a one-tailed test, this could be left or right. It doesn't matter. But we're not doing a one-tailed test. We're doing a two-tailed test. So we specifically need to focus on this row here. We're doing a two-tailed test, and our alpha is precisely this one right here. We have alpha 0.05 in this problem. Again, that's a recall of that. So we want to be working in this column right here. Now, which row we use is dependent on the number of degrees of freedom that are associated with the problem. So if you can recall, the number of degrees of freedom is the sample size minus 1. So our sample size here was 50, so the number of degrees of freedom is 50 minus 1, which is 49. Now, of course, for the sake of this video, this only goes up to about 16 right here. You got to look further on in the table when you have a degrees of freedom of 49. And when you look at that row with degrees of freedom 49 and seeing where that intersects with this column here, you get specifically the number 2.010. So 2.010 is the critical value you get with alpha being 5% with a two-tailed test and with 49 degrees of freedom over here. So this critical value is what's given to you in the table. Now here's where you have to understand what it is that you're doing. We have two critical values here. So knowing that this is symmetric about the t-value 0, this one's got to be positive, this one's got to be negative. Now notice none of the critical values in the table are negative. So you need to know whether you need to put a negative sign on your number or not. So of course this one's positive, so this is going to be 2.010. Then this is the opposite. And again, there was no negative sign on the critical number given to you in the table. You need to know that you've got to put that negative sign on it over here. So we've got negative 2.010 is the critical value over here. So we've got 2.010 and negative 2.010 as our critical values here. So if you're doing a left-tail test or a two-tail test, that means you're going to have a shaded region over here. You need to know that you need to apply the negative sign to the number that you get in here. So now that we've got this critical region completely labeled, let's now compute the test statistic.